Hi, this video is a continuation of a previous one where we looked at perceptron learning, and we concluded that the perceptron cannot be used to train an XOR function because, as we've seen earlier, it has a non-linear boundary. Now, the example we've seen last time for perceptron was the logical operations and OR and XOR. So your inputs were binary and your outputs as well were binary. So before going on to MLP now to see how we could develop a neural network to represent the XOR function, let's just look at another example for perceptron itself. So in this case, you can find we have two inputs here. Let's call this one x1 here, x2, and this is your y. So in case of your output, of course, it has to be as classes. So it can't be continuous because the perceptron output is a hard limit function. So you could use it to classify your data set into different classes. In this case here, we are considering two classes only, 0 and 1, but of course you can use the perceptron to classify your inputs into more than two classes. So this example is used to illustrate that your inputs could be actually continuous. As you can see here, x1 and x2 are not binary. We use the N and O logical operations as training set just to start off to provide us with very nice training set to get the concepts clear, but you can use any inputs, continuous and discrete as well. So in this case, this is a single data set here, which so after ending here, it continues on this side here. So we can see here in our data set, we have combinations of x1, x2, which leads to an output y of 1 and in some cases 0. So if you have a data set in this way, where two inputs or maybe at most three inputs, you can always represent your data set as a scatter plot. It's a very nice way to represent your data if possible. But like we said, if your data set goes to 4 dimensions or even higher, it becomes difficult to plot that. But just to illustrate what the perceptron is doing, so you could very well do that. If you're working with MATLAB, you can do that, or you could even do that in Excel, but just by doing sorting, and then you can plot all your data set which are corresponding to class 0 here. And then on the same plot, you can overlap the data set for the second data series for the class 1, and then you can see if you can put a straight line. So if you have a data set like this and you do training now for classification using the perceptron, expect it to be able to actually do the classification for you, because you can very easily put a straight line here. So I've done the training, and this is what the result was. But remember, the training depends on the initial values that you're using. So boundary you have here is not absolutely depends the amount of training you're doing and the initial values you have, but what you show is a perceptron is converging and it's able to classify the data set as follows. So you could be doing this training here in any software packages as freeware or in MATLAB or in Octave. You expect the perceptron to be able to classify this particular data set. So just go back here. The aim of this particular exercise is to show that your inputs do not need to be discrete as we had here. For example, for your take this example here, your x1, x2 here for the XOR were binary and output as were binary, but we have shown that your input can be continuous and still a perceptron is able to do the classification. Now let's move on to the MLP. This plot is simply showing to you that a simple plot. I like to do it in this way. So you could very well plot your desired output. So desired output are all shown as blue asterisks here, and your actual output, which your network is giving to you, is showing as red circles here. So if you just overlap both here over your, so in this case we had 40 instances in our training set. So it's what your 40 points shown, and then we are overlapping on the same plot here your output, the desired output, which are blue asterisks, and your actual output, which are the red circles. And we can see for every combination we have, they are exactly overlapping. If you had any case here where your neural network is not able to replicate your output for a particular combination of inputs, then you will definitely find that you're not overlapping. So I think it's a nice way for you to just a quick check. Now let's move on to the MLP. Again, coming back to problem of XOR, which we could not solve using the perceptron. The example shown here is a general MLP here, where we have input layers, output layer. We have a hidden layer now. For the MLP, we definitely need to have an input and then the hidden layer with an arbitrary number of neurons here, which we can, of course, change depending on the type of problem we have, and also on whether your network is converging or not. So if you're trying an MLP with a given number of hidden neurons here, you could increase that as well. Normally, your input and your output number of neurons would be fixed by a data set. Okay, the number of inputs you have, it is 3, 4, 5. So it's going to decide this one. Your output as well, the number of outputs you want to represent would also be determined from your process, from a training set. But the number of hidden layers you have could be 1 or 2, or the number of neurons you have in a given hidden layer that is subject to design, subject to testing, and see what is actually providing you with a satisfactory performance. Okay, now as mentioned earlier, the neurons in the input layer are non-computational neurons, so they do not have a summation here, nor is a weight here. They're just taking the input and feeding it into the next layer. So these are not non-computational neurons. These ones here in the hidden layer would be computational neurons, and the output layer as well will be computational neurons. So we're going to see as we go along what type of activation function we'll be using and what actually is the problem in applying the perceptron learning rule to the MLP. So the general procedure we'll be using to train MLP will be very similar to perceptron with some very important differences. So as we've seen earlier, we're going to use a net weighted input. So very similar here. We do the multi-product of each input with its corresponding weight. And after calculating this capital X here, we'll subtract the bias for a given neuron. And the first consideration for us would be what activation function do we use for the MLP. So as we go along, we're going to look at that. Now, main issue we highlighted in this part here, in this part we're saying here, let's just read together. So with a hidden layer generating its own set of intermediate output states, the computation of an error value cannot be done using the perceptron learning rule, since the desired value for these intermediate outputs are not defined in the training set. What are we trying to say here? Remember when we applied the perceptron learning rule, the correction in the weight or the threshold was alpha times x times e. Okay? So to be able to find the correction for a given weight or a given threshold, would need the error for that particular neuron. Now, how do you calculate it? How do you calculate the error? We calculate the error by taking the difference between the desired value, which is from the training set, and actual values the network is giving to you. So if you take a neuron, the output layer here, that's fine because you have all these outputs that are defined. You will have the desired value from your training set, and you will also have actual values. Actual value is available for all neurons. Anyway, when we start doing the training, as we iterate, we have the actual value. But the problem for these neurons that you have in the hidden layer, we don't have a desired value because these desired values are not present in your training set. This is why we call this one a hidden layer. So these neurons do not have desired values, they just have actual values, because as we send these inputs forward, we're going to see that later, we can very well calculate the output of each neuron. That's not a problem in the hidden layer, but desired output is not known. It means you are not able to calculate an error for the neurons in the hidden layer. That was a complication we mentioned in the last video. For over almost 10 years, people have been trying different ways to actually be able to correct for these weights here, because these weights are attached to the neurons in the hidden layer, and to be able to correct for this weight, you would need to have error. So in that sense, the desired value for these neurons, how do you get the error? So this is why it was quite an issue in the field of research to actually solve this problem and be able to correct for the neurons, these weights and threshold connected to the hidden layer. For the output, neurons output layer, so not much problem because you can define error here. So let's read that again. I hope it makes sense now. So with a hidden layer generating its own set of intermediate output states, the computation of an error value cannot be done using the perceptron learning rule. Since the desired value for these intermediate outputs are not defined in the training set, the only desired output that is defined is for the output layer. So several algorithms have been developed for learning MLP, but the most popular one, we're going to look at the backpropagation method proposed by Bryson and Ho in 1969. So remember, the Rosenblatt perceptron rule came up in 1960, and this was 1969. So you can see quite a bit of gap there, quite a lot of research being carried out. And it was quite a breakthrough when we could actually obtain convergence for MLP. So we're going to look at the backpropagation algorithm in detail as we go along. Okay. Now let's just put some notations now as we discuss forward the MLP. So if you look at this particle neural network here, where we have n inputs, so I'm going to call our inputs by index n, varying from 1 to n. For the hidden layer here, we're considering only one hidden layer for the time being. If you had more, you expand the notation. So in this case here, we are using the notation J, as J varies from 1 to m. And for the output layer, we're using notation K for any particular neuron, and K varies from 1 to L. So again, for the input layer, it's varying from, we're using the index I, as it varies from 1 to n. For the hidden layer, J varies from 1 to m, and for the output layer, K varies from 1 to n. So just bear that in mind as we go along, we'll be using these notations. So just look how actually each of these weights now are labeled. So any weight between two neurons is going to be labeled by W for the weight, and then we use the index I and J here. So it is just the two neurons that are so the I and J here are the two indices that we have for the two neurons on either side of the weight. Okay. So similarly here for this weight that we have in general here between neuron J in the hidden layer and in neuron K in the output layer is called WJK. So we'll be using this notation here. So that's a very efficient way for us to refer to any particular weight. Now, as for the threshold, so the threshold here is simply going to be labeled by the particle neuron we are going to use. So we'll come back to this later. As for the outputs here, we know the output would be on the output layer itself. So this neuron 1 here in the output layer is Y1, then 2 is Y2, K is YK, and L is YL. Okay, so we can use this notation here. So we've discussed that already. Now, once you have these outputs Y1, Y2, and YL, so I'm beginning to refer to this particle notation again and again. So I want to make sure you're comfortable with that as well. I'm going to refer to this diagram a lot, so that we have to make sure we are referring to the proper part of the neural network again and again, so that we don't get lost. Very easy to get lost here as we go along, and to make sure we're getting the proper equations, we have to always refer to this neural network. So the error signals here is E1 to EL, is simply referring here to the errors for every neuron you have in the output layer. So as you have L neurons output layer, so you have L errors. So every neuron here would have its corresponding error, because each of the neurons in the output layer, of course, remember, they have their value in the training set. So I would say here WIG denotes a weight for the connection between two neurons. So it's going to be the previous neuron and the next neuron, because an narrow weight is going to always be situated between two neurons. Yep. So when we talk of WIG here, so I is for the input layer, J is for the hidden layer. So WIG would be a weight linking a neuron from the input layer to the hidden layer. And WJK, similarly, since we use J for the hidden layer and K for the output layer, so WJK would be a notation for weight between the input layer and between the hidden layer and the output layer. Okay, so let's pursue ahead. Now, remember, we're using the index K for the output layer, so we are able to calculate an error for the output layer. This is possible. Like we said, for the hidden layer, we can't, for example, find an EJP, because for J is a hidden layer and we don't have the desired value. So to start off, once you're able to calculate the actual value that you're obtaining for a particular neuron in the output layer, and we know P are the iteration numbers. So don't worry about P for time being, because we know we're going to iterate just like we did for the perceptron rule. We're going to go through the training set again and again over different epochs. So P is simply saying here we are at a particular iteration number. Okay, so as we feed our input signals through our neural network, going of course through the hidden layer first, and then from the hidden layer you go to your output layer. At the output layer, you are able to find an error K for the output layer neurons. This is possible. Okay. Now we'll discuss this one. Why we now need to propagate an error metric back to the hidden layers, because we don't have an error metric for the hidden layers. If we did have an error metric for the hidden layers, then we did not have to do that backpropagation step. So we understand as we go along, what does backpropagation means? What are we trying to achieve by doing backpropagation? And we're talking about an error metric. So we're not going to actually backpropagate the error itself. We're going to backpropagate actually an error gradient. So through research has been shown that if you backpropagate the error EK itself, it doesn't provide a good metric for convergence of a network. But if you were to backpropagate something known as an error gradient, it's a much better indicator of error. So basically here, if we go back to the network, we're going to start here off with a value of x1, and of course all these weights here, remember, just like we did for the perceptron, would be given initial values as well as the threshold. So if we have values for all the weights in the threshold, and we know what the activation function is, and we have values for x1 to xn here, we can simply activate the neurons and calculate the output for all the neurons in the hidden layer. So once you have all the outputs of the neurons in the hidden layer, then these outputs actually become inputs for neurons in the output layer, and you can again, of course, all these weights would again have values, and all the neurons in the output layer would have a respective threshold. So now, based on the outputs of the neurons in the hidden layer and the weights and threshold, you're able to finally get your output, the values for your output at the output layer. Of course, if you had two hidden layers, then you need to keep propagating from the first hidden layer to the second hidden layer, and then from the second hidden layer to the output layer. But in this case, we have only one hidden layer. Now let's come back to the error gradient we mentioned. Remember, we've said we need to backpropagate an error metric from the output layer towards now the input, going for the hidden layer, for the simple reason that we do not have an error value for the neurons in the hidden layer. So let's look at that error gradient in more detail. So the error gradient is determined by multiplying the differential of the activation function and the error of the neuron output. So let's read that again. So if you wanted to calculate the error gradient for a particular neuron, it's obtained by multiplying the differential of activation function, because it's looking graded here, and the error of the neuron output. Okay. So this implies that we need to use a transfer function or an activation function which is differentiable, because from the very definition of error gradient here, we are saying we need to multiply the differential activation function. It means we have to choose an activation function which is differentiable. It's for this reason that we can't go for the step or the sign activation functions. So we're going to now use a Sigmoid activation function, which we've already come across as we're discussing various activation functions. And this was the forms here that we obtained for the Sigmoid activation functions with different value of theta. So we've already seen that as your input x varies from -infinity to infinity, your output is bounded between 0 and 1. That's very interesting here. So in this case, we're showing here the activation function when your theta is 0, and then when your theta is 5, for example, then you see simply shifting the whole curve right or left if you choose different values of theta. Okay. So an important point here is this activation function here. This graph is fully differentiable at any point because it's a continuous function. It's not like the step function or sign function, which is a hard limit function. It's not differentiable at the point of transition. If you differentiate a step or sign activation signals, you just get 0, infinity, and 0. So there won't be any intermediate gradients, so it's not usable if you wanted to differentiate the activation function. The next step here is, let's see what do we get when we differentiate this signal. Okay. So you can work it out. So I've seen on this slide here, determine the differential of a Sigmoid activation function, express it in terms of y. So the good thing is when you try to differentiate the Sigmoid activation function, you can very well express the result, not in terms of x, but in terms of y itself. So I'll leave that up to you. If you differentiate that using different methods, you could use the train rule, for example, you're going to get this result here, e power minus x over 1 plus e power minus x 2 squared. And if you now try to formulate this output here in terms of y, you're going to get y times 1 minus y. So I'll leave that as an exercise for you to show that from this result here, you can go to this form here where you're expressing the differential of activation function in terms of your output. Now, this is very interesting for us. It means if you want to work out the differential of activation function and use the output, you can just calculate the differential from the output values only, don't need the input. Okay, so we'll come back to this result as we go along. Now, if you look at this particular formula here, this equation is very similar to the perceptron learning rule, where you're correcting for weight somewhere in your network by taking the old value and adding a correction factor here, which is computed in the perceptron learning rule. Remember, the correction was calculated by finding alpha xe. Okay, So for the MLP here, we're not going to use E because for simple reason we don't have E for the hidden layers. So if you look at the notations now, we've come across before. So again, let's just show that neural network here. We are talking of WJK here. So JK is a weight that's sitting between the hidden layer and the output layer. So for this particular weight here, definitely you can't use the input values, because for this particular weight here, the input is actually the output of a hidden layer. This is what I'm just putting this point here to calculate the weight correction delta WJK. The input signal Xi cannot be used because it do not feed the output layer directly, unlike the perceptron. So for the perceptron, there was just one neuron, so the input was actually the input in training set. But when you are dealing with an MLP, you have to be careful what input you're using. So this is why I'm saying every time you have to refer to your network, your neural network, carefully to see what are the inputs you're using. For example, for this particular way that you have here, your input is actually the output of this particular neuron in the hidden layer. So this output here would be, this output is YJ. This output is actually the input, the weight. So if you're applying the correction for delta WJK and you apply alpha X times E, so your X will not be from your input layer, but will actually be Y. This is why we're writing this here. So we've already mentioned we're going to use error gradient delta instead of the error itself. Okay. And we're going to modify the perceptron learning rule as follows. So before it was alpha XE, now we have alpha. Your X becomes YG, I will just describe. You have to take the input for that particular weight. So in this case, the input to the weight WJK is YJ. And you can find here your error, which was EK, has been replaced by delta K now, where delta K is the error gradient of a neuron K in the output layer. So if I go back here, we're talking of these neurons here. So if you're talking of a specific neuron here, from the equation we've just derived, I just go back here. So it means you're able to work out from this definition here of the error gradient is obtained by multiplying the differential activation function, which we've just obtained here, by the error. So error will be EK. So if you know error EK here, then simply the delta K for this particular neuron is going to be the differential activation function, which we just said is y into 1 minus y, so it becomes yk into 1 minus yk, and then multiply that by the error signal for that neuron, so it's just going to be simply here ek. So if you wanted to calculate, for example, delta 1 for this particular neuron, it's going to be y1 into 1 minus y1 times e1. Similarly, delta 2 is going to y2 into 1 minus y2 multiplied by e2, and similarly, you can just follow through here. So you can see here, it's not difficult to calculate the error gradient for neurons in output layer because you know the error and you know the output definitely. The complication would still be there. How do you calculate these error gradient for neurons in the hidden layer? So basically, we're going to, like we said earlier, we're going to backpropagate these error gradients towards hidden layer to get an estimate for the error gradients at these neurons. So we see how we do that as we go out. So I hope this equation is clear now. If you again remember how we did it for the perceptron with alpha XE, now it's going to be alpha, your X becomes YJ because this is the input to this particular weight, and the error gradient now for that neuron is delta K here because we're talking of the weight delta WJ. Now the question is, how will adjustment for weight linked to the hidden layer neuron be calculated? So we are able to find the correction for all these weights here which are connected to output neurons because you know the error gradients of these ones. If you look at this equation here, we're simply saying we can correct for all weights if we know the output and we know the error gradient of that neuron. Now, if you were to correct now these weights that you have here, you definitely know the inputs to them because these are the inputs to these weights that connects your input layer and your hidden layer, but we don't know the error gradients of these neurons here. So how we'll do that? So again, like I mentioned earlier, we're going to backpropagate these ones. So we'll see how do you actually do that as well. Okay, so the weight correction for a neuron in the hidden layer is calculated as follows. So if you extend this equation we've seen here for JK, now if you want to do it for WI, ij in general for any weight that you have sitting between the input and the hidden layer. So if you just extend that straightforward, you're going to get that equation. Is alpha x now, this is x now because wij is connecting your input to your hidden layer, so your input is actually xi, and then you would have to work out the error gradient at that neuron. Yeah, you would need to work out the error gradient of this neuron here, so delta j. Okay, delta j are the error gradients for neurons in the hidden layer. So we still face a fundamental problem in calculating the error gradient for the hidden layer neurons because they do not have associated errors. If we just go back here, I want to make sure you understand this part here. If you see how we calculated the error gradient for a neurons output layer, it was about finding the product of the differential activation function with the error. So we still do not have an error for the hidden layers. So now how do you actually find this delta j here? This is what we're going to do next. So delta j would be actually the product of y into y minus y. That is fine. We've just worked out this result here. This is a differential of the activation function. We are talking of j here. This is why you have yj and yj. So it's the outputs of that particular neuron in the hidden layer. Now, normally we need to have ej here, but since we don't have ej, what are we doing now to find a representation, if you want an alternative metric for the error value? ej, we are back propagating the error gradients from the output layer to that neuron. So instead of ej here, we are representing aj by this parameter here. So let's look a bit in detail what are we actually doing here. So we are back propagating delta k of error gradients that you have in the output layer, and you're back propagating these error gradients not just like this, but through the respective weights. So if you wanted to calculate, for example, the error gradient for this neuron here, so you will take output. So if you call this one here y1, so y1 into 1 minus y1, that is clear. This is a differential activation function, but you need to multiply that by e1, but we don't have e1. So what are we doing here? We are simply back propagating all the error gradients which are connected to this neuron. So it is delta 1, delta 2, delta k, delta l for the respective weights. So if you take delta 1 here, you're going to multiply it by this weight here, and then delta 2 times this weight here, times delta k times this weight here, which connects to this neuron, and similarly delta l times this weight here. If you wanted to find, for example, the error gradient of this neuron here in the hidden layer, you would multiply here delta 1, but not by this weight, of course, but this weight which connects to it. Similarly, you're going to back propagate by this path here, by this path, and this path. And similarly, if you want to work out delta j here, you're going to back propagate this signal here through this weight here, this weight, and this weight. So this is what this equation is saying here. This is the back propagation part here, where we're taking the error gradient in the output layer. So delta k corresponds to error gradient in the output layer, and multiplied by the respective links that connects this neuron in the hidden layer to that j here, because you're working out the error gradient on neuron j in the hidden layer. So it is all these weights here which links your hidden layer to your output layer. It's not difficult to implement. Actually, as we go along, it's going to become much simpler. Yeah. So let me repeat that again. If you wanted to work out error gradient for any neuron, you would just take the differential activation function. So that's this part here. But ideally, you would want to work out the error of the neuron, but since for the hidden layer it's not possible to do that, we are back propagating the error gradients already computed for the output neuron. Because output neuron have errors, we can work out the error gradients at the output layer, and then once we have these error gradients at the output layer, we can back propagate them through the respective links towards that hidden neuron in the hidden layer. Okay, so again, just bear that in mind. We're going to come back to this later as we look at one example. It's not difficult to actually compute. Now, once you have an error gradient, you can very easily now adjust the weights and threshold connected to a given neuron, like we've seen earlier. So this equation is trying to calculate the correction factor for a weight between your hidden layer and your output layer. So anyway, this weight here is connected, is feeding, if you want, a neuron in the output layer. Okay. This is why here you're using the error gradient for that neuron here, so delta K. And since it's the input now would be the output of a hidden layer, so we have seen that equation earlier. And if you want now to correct a weight that's sitting between your input layer and your hidden layer, so I is the input layer, J is the hidden layer, so it's against alpha, and now your input would be a proper input. That's the input to your hidden layer, and you're going to use delta J now, which is error gradient on the neuron in the hidden layer. Now, what about correction for threshold for given neuron? Now, just like we did for the perceptron, we already discussed how do we apply the same principle that we use for the weight correction to threshold. So a small mistake here. I'm just going to correct that quickly. So then input of -1. Input of 0 is an input of -1. We've seen that earlier. So the way we're going to correct the threshold is very simple. We're going to treat now the base theta as a weight. And in that case, since we're always subtracting the theta, we assume the input to be -1. If you apply this same principle here, and we want to write expressions for delta theta, for example, jk. So it's going to be very similar here. You have alpha, and then your input is always -1, and there's going to be delta k. Similarly, if you wanted to correct delta theta for a given neuron, the hidden layer, so it's going to be alpha. Now you input again -1, and that's going to be delta k. So it's very easy now to extend from the correction expressions for your weight to your threshold. Now, as an exercise, if you want, you can work out the correction for these different, for this particular neural network here. So just see how I have labeled neurons now in this particular MLP. So the neurons here for the input layer are 1 to 4, and then I continue in the hidden layer. We continue from the 4, so we get 5, 6, and then for the output layer we have 7 to 10. So in this way here, like we said, this is how we label now the various weights. So this weight here is going to be called W15, and this one W46, but similarly any other weight now, for example, this one is W36, W35, so all the labels become unique in themselves. So similarly, if you want to label these weights as linking your hidden layer to your output layer, this is W57, W6,10 here, and then W69, 68, and so on. So you can see all the labels are unique. Similarly, I've not shown on this particular neural network all your threshold. So this threshold here will be a theta 5, this one theta 6, this one theta 7, theta 8, theta 9, theta 10. We remember, as we are doing the learning process, we have to correct the weights and the threshold. So we are trying to put unique labels for each one of them, which we can refer later. Okay, now how will actually the training take place? So like we said, all these weights here would have values assigned to them, as well as all the thresholds. Okay, now once you are given now an input for a given set, you can very well work out the output of this neuron here in the hidden layer, as well as this one. So let's call this one Y5, Y6. So if you wanted to calculate Y5, for example, so it's going to be X1 times W15 plus X2 times W25 plus X3 times W35 plus X4 times W45. This is where you get your capital X5, you can call it, and then you need to take capital X5 minus your theta 5. This is what you get as X minus theta, and then you feed that the difference to your Sigmoid activation function to get Y5. Similarly, if you wanted to find Y6, so you have to find your weighted sum first. So you can take X1 times W16 plus X2 times W26 plus X3 times W36 plus X4 times W46. This is your capital X, and then you have to subtract, of course, theta 6 now. This is your X6 minus theta 6, and then you use that into your activation function to get Y6. Once you're able to find Y5 and Y6, then you use this one now to calculate Y7. Let's do one of them. So Y7 is going to be Y5 multiplied by W57 plus Y6 times W67. So this is your capital X7, then minus theta 7, then you feed that to Sigmoid, get Y7. Similarly, you can work out Y8, Y9, Y10. So once you have these different values, and Y7, Y8, Y9, Y10 would have a desired value training set. The difference now, actual value and this desired value. Actually, it's a desired value minus actual value. You get errors here, so you can work out E7, E8, E9, E10. So once you have here all these values here, you can work out now delta 7. So delta 7 is going to be, like we said, Y7 into 1 minus 1/7 times E7. Y8 is going to be delta 8, so is going to be Y8 into 1 minus Y8 times E8. So similarly, delta 9 is equal to Y9 into 1 minus Y9 times E9, and your delta 10 here is going to be Y10 into 1 minus Y10 multiplied by 10. So you are able to calculate your delta 7, delta 8, delta 9, delta 10. Okay, so I'm inviting you to be able to write all these expressions for error gradients, correction factors, and so on. So this is what I'm reciting now, but you give it a try. Now, once you're able to find delta 7, delta 8, delta 9, delta 10, the next step, immediately now you can correct for all these weights and threshold that are linked to this neuron. So you can work out delta W57, yep, delta W67, based on the equation we've seen earlier, and you can also correct for delta theta 7. So similarly, if you know your delta 8, you can correct for these two weights and its threshold. If you know delta 9, you can work out the correction factors for these two weights and threshold of theta 9. If you know this delta 10, here's error gradient, you can work out the correction factors for this weight here, W610 and W510, as well as theta 10. So this is part of it. So it means at this particular iteration, you'll be able to correct for all these weights and threshold. Now, the next step, like you've seen earlier, to be able to correct these weights now, you would need to know delta 5, and you apply the same process. Now, if you want to work out delta 5, it's going to be Y5 into 1 minus Y5 times E5, but we do not have E5, so we're going to backpropagate these error gradients in the output layer towards delta 5, towards the neuron 5. So how we do that? You can see here this neuron 5 is linked to these 4 other neurons in the output layer through these weights. So in a way, we're going to say now your E5 is going to be replaced by delta 7 multiplied by W57 plus delta 8 multiplied by W58 plus delta 9 multiplied by this weight here, which is W59 plus delta 10 multiplied by W510. So this is going to be this term. Remember earlier we had this sum here. So if you were calculating here delta 5, so it's Y5 into 1 minus Y5, fine. And then this term here is what I've just told you, how you backpropagate all the error gradients in the output layer towards your input layer, but through the respective weights. So the same process you've done here, you can very well do the same thing with delta 6. To calculate delta 6, so it's going to be Y6 into 1 minus Y6 multiplied by all these delta 7, delta 8, delta 9, delta 10, but through their respective weights. So you're going to use these weights here. Now, once you have delta 5 or delta 6, then you can correct for all the weights and thresholds linked to that neuron. So once you've got delta 5, you can correct for this weight, this weight, this weight, and this weight using equations like this. Okay, bearing in mind, of course, you have to use the correct inputs to that weight. So for for neurons in the output layer, the weights are going to be fed from the hidden layer, and for weights for neurons that are in the hidden layer, so all the weights that are feeding the hidden layer would have inputs from the input layer. Okay, so you are encouraged now to write for this particular neural network all these steps. Okay, so let's look now at how we actually go about to do training for MLP in more details. Okay, just to formalize the process. So learning in MLP proceeds the same way as with perceptron. So you have a training set of patterns which you're going to feed constantly over many epochs and over many iterations through your neural network, and at each point you want to adjust your weights and your threshold. Now, in the backpropagation neural network, we've seen we have 2 distinct steps. We have to first feed forward the data to be able to get to errors, but that's not the end of the story. You have to backpropagate your error gradients to be able to work out error gradients in your hidden layers. So the network propagates the input pattern from layer to layer until the output pattern is generated by the output layer. If this pattern is different from the desired output, so you always calculate an error parameter, and from this you work out an error gradient for your output layer, fully possible, because you know the desired output for your output layer. And for your hidden layer, you backpropagate like we've discussed already. Now, once you know the error gradients for all the neurons, you can work out the correction factors for all the weights and threshold linked to that neuron. Okay, so basically, if we just list down all the steps that you have to follow to do the MLP training, so they're as follows. You would definitely have an initialization step where you give values to all weights, so random values to all your weights and threshold. This is important for you to be able to activate your neural network to be able to get outputs for neurons in your hidden layer and from your hidden layer to your output layer. Okay, so you activate. Once you do the initialization, you activate, you get outputs for all your neurons. So this is how you're going to do it. So this one is showing the computation of the output for neurons in the hidden layer. Once you get to capital X minus theta, you feed that to your sigmoid, and your sigmoid is 1 over e power, so 1 over 1 plus e power minus x. So that minus x there is actually this term you're getting here. So once you're able to activate all your neurons in your hidden layer, you can use now these outputs to activate neurons in your output layer. Okay. Now what you find here is xjk is nothing but the y. Yep, it's a general term here, but we have seen that the outputs from the neurons in the hidden layer actually are inputs to the neurons in the output layer. Yeah, that's what I'm trying to say here. Once you have used x1 to xn to work out the outputs of these neurons in the hidden layer, now these outputs will be used as inputs to the neurons in the output layer through the respective weights. Now, once you're able to do that activation, like I've said for the network we've seen earlier, you're going to work out the error at the output layer. From the error in the output layer, work out the error gradient in the output layer. At this point, if you want, you could correct for all the weights and thresholds, correct the neurons in the output layer, or you could work out the error gradients in the hidden layer as well and then correct all the weights. It doesn't matter which way you go, but once you're able to work out the error gradient at a given neuron, you can immediately correct for its weight. Okay. So once you can calculate the error gradient for neurons in the output layer as follows. So you work out the error first, and then your delta k, and then you would calculate the weight and bias correction for neurons in the output layer. So like I said, once you know your delta k, you can work out the correction factors for your weights corrected to the neurons. So this is for the weight, and once you have delta w jk, you would just add it to the previous value to get the new one to use the next iteration. And if you just extend this equation here, we have for the weight to the threshold, we are just replacing here your input here by -1. Let's say we've already discussed that. How do we extend the expression for the weight to the threshold? And similarly, once you have a correction factor for the threshold, you will just add it to the previous value to get the new value for the threshold that's going to be used in the next iteration in previous one. Okay, now next step, we have to backpropagate our error gradients towards our hidden layer. This is what is showing here. Now we've discussed that elaborately. So this term here is again an alternative to the error for neuron in the hidden layer. It's simply backpropagating the error gradients through the respective weights towards hidden layer. And this one is the differential of activation function on that particular neuron. Now, once you know delta j, similarly now you can correct for the weights and threshold that's feeding that particular neuron. So bearing in mind now your input is actually the input the neuron. And if you extend that now to get your threshold, you just replace the input by -1, and delta would still stay. And you would update again the weight and bias simply by adding its previous value. So this delta w, delta j is from here, and then you just add it to the old values to get the new values, and then you will iterate. Yeah, so then you're going to iterate as many times as required that you obtain convergence. And we've discussed how we can assess convergence is by looking at the absolute error, or mean square error in your output layer, and then you can decide when to stop. You can set the conditions for that. So let's apply all these different procedures now to the exo function, which we could not solve using perceptron. Now the particular MLP I'm choosing here, since we are choosing 2 inputs, so that's definite, you have 2 inputs here. You have only 1 output. This is why I have only 1 neuron in the output layer. But the number of neurons you are choosing in the hidden layer could be 1, could be 2, could be 3. You can play around depending on what's the convergence to you. Now, in this case, you are choosing 2 neurons in the a hidden layer here. So by labeling the neurons as follows, so 1, 2 in the input layer, 3, 4 in the hidden layer, and 5 in the output layer, you will now get these labels for your various weights. So W13, 14, this one, so it's 23, 24, and these two weights here linking your neurons from your hidden layer to your output layer, W35 and W45. Now, again, I'm recapping on that. Like we've seen earlier, these two neurons are non-computational neurons, so they don't have any threshold or any weights here. Whereas these neurons here, 3, 4, and 5, they are computational neurons, so they would have activation functions, and they would definitely now have their thresholds, which we are labeling them as theta 3, theta 4, and theta 5. Now, based on this this neural network here, you can very easily write expressions for Y3, Y4, Y5. This will be the activation step. So let's just do that orally, but you could do that and write down the expressions. So Y3 is X1 times W13 plus X2 times W23. So this is a weighted sum. You will get a capital X3 if you want to call it, and then you will going to subtract theta 3 from this one, and then you will feed that your sigmoid activation function. So similarly, if you want to work out Y4 here, you have to work out first capital X4. So it's just going to be X1 times W14 plus X2 times W24, and then you take that capital X4 minus theta 4. This result now is fed to sigmoid activation function. Then you are able to get Y3 and Y4. Now, if you want to work out what is Y5, let's work out capital X5 first. So it is equal to, remember this output here of neuron Y3 is Y3. So it's Y3 times W35 plus Y4 times W45. That's your capital Y5 minus theta 5. This difference now is fed to your sigmoid activation function to get Y5. Once you're able to get Y5, you can very easily now subtract this Y5 for a particular iteration step here, for a particular combination or instance in your training set. These are actually your YD, and you obtaining the actual value here. You could work out now E5. Okay, so let's see how this works for one instance of the training set. So we're choosing here X1, 1, X2, 1, and Y0. So we're choosing this particular combination here just to illustrate steps. And these are the values I have set randomly. You could use other values if you want. So like I've said, to be able to activate to function your neural network initially, you would need to have random values assigned to your weights and thresholds. So all these weights here come from this diagram here, and we're given values in them. These are the expressions I've just explained to you. How do we get the Y3, Y4, Y5? So I've done that orally, but these are now the expressions written down. So if you replace the values we have for X1, X2 as per the training set we are using, and these values for the initial values for your weights and threshold, you just plug in here. These are the values you're getting. Now remember, sigmoid means 1 over 1 plus e power minus x. So this is your x now. This is what you would have to replace in the expression. So cross-check that you get these values, and once you get your Y5, if your Y5 is here, so this is the actual output of the MLP, and the desired value, if you go back here, the desired value for this combination was 0. So this is why we have a 0 here. Subtract the Y5 you're getting from your network at this point, you get an error of minus 0.5907. Next step, you work out the error gradient, which was Y5 into 1 minus Y5 times error. So for the error gradient in the output layer, you can use the error set because it's available. And so you just replace the value you get for Y5 into 1 minus Y5 multiplied by the error, which we got as minus 0.5907. So this is what you get error gradient at this point. So at this point, it means you can correct. Once you've got the error gradient at neuron 5, you can correct for W35, W45, and theta 5. This is how we're going to correct it. It's alpha times Y3, because remember the input to this weight here, W35, is Y3. So from the neuron in the hidden layer, which is neuron 3 here. So Y3 will work it out. Before it was 0.5250, so this is what's coming here, and multiply by delta 5. We are choosing a learning rate of 0.1. Like we said earlier, this value is set adaptively actually in advanced optimization algorithms, but here we're just setting this value to 0.1 just to illustrate the calculation steps. And anyway, we're not going to play around with alpha during the training here. We're going to illustrate later. So like we said, this factor is actually optimized using other methods, which we're not going to cover here. So if you apply this equation here, you get the correction factor for weight W35, a value of minus 0.0067. Okay, similarly, you can work out the correction factor for weight W45 using learning rate again of 0.1. Now Y4 we work up before it was 0.8808, and then delta 5 is as calculated. So similarly, it's minus 0.1274. So we get this value here. So similarly, we can correct for the threshold theta 5 here. So alpha, your input is always minus 1 for threshold, delta 5 again. So again, once you work out delta 5, you can correct for this weight, and the threshold linked to this particle neuron. So we're getting a value of delta theta 5 of 0.0127. So next step, you could of course immediately get the new value for this threshold. Yeah, but we are proceeding now to get the correction factor for all the weights and then adding afterwards. But you could very well at this stage here work out the new value for W35, W45, and theta 5. Now, to work out delta 3 means error gradient at this neuron here in the hidden layer. So it's as before, y3 into 1 minus y3. But since we don't have E3, we're back propagating the error gradient. In this case, of only one neuron in the output layer. But if we had more, which we know we have to back propagate all the various error gradients for respective weights. So in that case, it's quite simple. We're just propagating delta 5 through W35. This is what delta 5 through W35, and we get this value here. Means we get delta 3. Once you get delta 3, it means you can correct for theta 3, W13, and W23. Now, in a similar way here, we can work out the error gradient at neuron 4. So it's y4 into 1 minus y4 for this one, times we're back propagating delta 5 now through this weight W45, this term here. So we know delta 5 from the previous step, and we know W45 is the value of this weight here, and we get a value of delta 4 of minus 0.0147. So you can cross check all these values. Okay. Now, once you work out delta 3, like I said, you can correct for this weight, and theta 3. That's what we're doing here. Bearing in mind now, of course, the input to this neuron is x1 or x2, depending on which weight you're correcting. So if you're correcting for weight W13, so this one, the input is x1. Okay. And your alpha and delta 3 would be standard because we're talking here of this particle neuron 3. So in this case, just x1 is going to change. If you want to correct for the weight W23, which is also connected to this neuron 3 here, you have to use x2 in that case because the input is x2. Now the values are same for alpha and for delta 3. If you want to correct for the threshold theta 3 here, is alpha, the input is always minus 1 times delta 3. So this is what you're getting. Okay, now see, once you know delta 4, like we said, you can now correct for W14. So it's a correction factor for it. So alpha times, of course, input is x1 times the delta 4. You get this value. W24 now, which is also connected to neuron 4. W24 so it's alpha times x2 times delta 4. And if you want to correct for the threshold theta 4, again, your input is always minus 1 for these values. And then the approach we've taken here is once we got the correction factors, then we just keep adding it to all values here. So once you get delta W13, you add it to the previous value to get the new value, and you do that for all the different weights and all the thresholds. So that completes one iteration. Now, what is shown here is once you have the previous values, okay, you can now feed in the next instance in the training set. So we have chosen here x1 is equal to 0, x2 is equal to 1, and y is equal to 1. And just check it down. So x1 is 0. So we are now taking this one. Okay, and you can see here your output is 1. Your output is 1. So you could now use these updated weights and thresholds to work out for the next one. Okay, so it's an exercise for you to try to use this one. Now you can clearly see here, as the example I've just illustrated, you don't actually need to feed the patterns in any given order. Yep, so we have chosen this one. You could have reshuffle this training set to put 1, 1, 0 on top, and then to have 0, 1 next, and so on. Yeah, but important here, this is one epoch. So one epoch in this case would be 4 iterations, and when one epoch is finished, we have to feed these 4 combinations again and again. Okay, so as an exercise, you can just work up this one on your own and see if you can use that one. Of course, you're going to use updated weights now. Okay, so at this point, updated weights for use in next iteration within the same epoch, and ultimately another epoch is started to continue training the MLP. The sum squared error is a useful indicator for network performance and to assess when you stop iterating. So I prepared a small worksheet here, very similar to what we did for the perceptron, which was quite a bit more complex. And I'm just going to show that to you now, and you can work out a similar worksheet. But in practice, of course, you will not be using such as a worksheet to solve your or to train your MLP. You're going to use other platforms like MATLAB, Octave, or there are other environments in Google now which you can use, or any open source software which can be used. But this worksheet illustrates very well the calculation steps we've illustrated, and it will not include, of course, the advanced optimization methods that are used to provide quick convergence. But for your case, here's a good. I'm just going to shift now to the worksheet to illustrate the steps we have for this particular neuron we've just looked at, for this particular new MLP that we have just discussed. So we have W13, 14, 23, 24, 35, 45, and the threshold theta 3, theta 4, and theta 5 to adjust as we go along the training. But you can very clearly see here, if you were to change this network architecture and have only one neuron here, your worksheet will be very different. Or if you include 3 neurons in your network, so your neuron, your worksheet will have changed quite drastically. So the worksheet is not very useful for that. But again, I'm saying we are using an Excel worksheet here just to automate the steps that you can cross-check answers and also see how actually the training is being done in a principle way, in a basic principle. So I'm shifting now to the worksheet. This is what I've prepared for you in terms of worksheet. So you can see here, this first column here is your iteration numbers, simply using alpha 0.2 here, which can play around and see what happens. So highlighted here in yellow is the first epoch, if you want. So you can see the order, it doesn't need to be like we have in the truth table, it can be in any particular order. As you just do, because we have already worked out this one in detail, and I'm asking you to use this one now so you can cross-check your answers from the worksheet. And you can see here, this highlighted in green here is a second epoch. So once you finish this iteration, of course, you will continue in the next epoch and you will feed that data continuously. And for training an MLP, it's not uncommon to go over 10,000 epochs. Is quite common because training is going to take much more time here. It can also go quicker depending on your data set, but it can also take much more time to have convergence. Now, as we've seen, the first step is you have to give initial values to all your weights and your thresholds. So these are these values here. Once you have worked up these values, you can now simply work out the values of your output first in your hidden layer. This is what's shown here. So you're taking the product of the inputs with the weights and then subtracting the threshold and then feeding that into your sigmoid. So similarly, you can work out Y4. Once you know Y3 and Y4, you can work up your Y5, which is going to use now, if you look at it, it's going to use Y3 and Y4 now as inputs. Once you are able to work up your Y5, which is the final output of your network, you can work out error by taking the difference of your desired output and your actual output. So you get an error here. Now, once you find this error here, first the error gradient you have to work out has to be delta 5. So you can't work up delta 3 without delta 5 because you backpropagate delta 5 to get delta 3. So this one is simply calculating Y5 into 1 minus Y5 multiplied by the error you just got, so E5. So once you've got to delta 5 here, you can work up now delta 3. Okay, you can work up delta 3 by backpropagating the delta 5 through the weights, and of course multiplying here by Y3 into 1 minus Y3. If I double click here, you're taking Y3 into 1 minus Y3 multiplied by the respective weight times delta 5. So you work out your delta 4. Now, once you know all these error gradients, you can correct now for all your weights and your thresholds. Yep, so we've seen how to do that. You can implement the expressions we've seen in your in the presentation. So once you're able to get all these final weights here, you can work up, of course, an error you're getting. I'm saying sum square error here, which is the error you should find here. Yeah, so sum square error. Or you could use absolute value as well. Now, next step, of course, to get the value of your weights in the next iteration, like we've done earlier, you're just going to link these two. So you're going to take this value and bring it down here and just work it up. Similarly, to get W1 for the new value is going to bring this one down. Very similar. So for all these values that you have from here to here now, they are simply bringing down these values from the previous iteration to get the updated weights and thresholds. And then you just, for the same step, to get Y3 now, Y4. So if you write expressions for the previous year, you can just drag down to get the new values. And the sum square error here, you can see I'm just squaring the error, so we just get the positive sign. Okay, that's what we're doing, because we have said you need to take care of the sign of error, because if you just add errors together, you can get an error of 0 over a given epoch, but doesn't mean that the absolute values of your error were the values of the error were actually 0. So you have to take care of this sign of error as by squaring it, writing the absolute value, absolute error, and then as you plot iteration now against this error here, as you iterate, you find this error is dropping, but quite slowly and sometimes increasing. So let's just shift back now to the lecture slides to discuss what results I got by carrying out iterations quite a long time. So basically, you're going to copy, if you want to use Excel sheet here to do the training over more number of epochs, you just have to copy the same training step over and over again, and then the same equation you have would be relevant. As you drag down, it's going to solve for the it's going to adjust the weights, and you can see if you're getting network convergence. Okay, so let's shift back to the PowerPoint slide to show you in general what result I got. Okay, so we're back to the slides now. So you have had a look at the worksheet, which you can, of course, I would encourage you to do that and to cross-check your answers which you're getting. You would see very similar for the step you have just covered, these ones, you can cross-check these values in there. And for the one I've asked to do, so I would encourage you to do by hand first, and then you can cross-check your values from the worksheet. And then next exercise you can do from the worksheet is try to see when you get convergence. So what I've done here in the following slides, I have actually plotted all the various convergence of your error for different learning rates. Okay. So this is what I've got for learning rate of 0.1. So you can see the error initially increases and then starts reducing. So this is 4,000 iterations here. And then if you choose a learning rate which is 0.3, of course, it's going to converge quicker. That's normal, but you have to be careful about the learning rate. It can also cause instability. And this is for learning rate of 0.5 and a learning rate of 0.7. Yep. Okay, so just like we've done earlier, after you have done the iteration and you're happy with the you're happy with the network, it has converged and your error is within the limit you want, then you can just take the weights and the thresholds that you get in the final step where you stop, and just replace that in your network, in your MLP, and this should be your train neural network, which is being used to replicate your process. So you will have a very similar process we've done earlier. Okay. Now, in this last slide, the choice of a learning rate needs to be done carefully, as high learning rates can lead to instability in the network, and the network may not converge. So you have to be quite careful about the learning rate. But typically in advanced optimization methods or in the software packages, this learning rate is taken care of for you, because you use adaptive algorithms to actually dynamically modify the learning rate, which basically is dependent on the rate at which your gradient is changing. And there are other methods you can use to accelerate your learning of your MLP. For example, there's one activation function called tangent. So it's not the Sigmoid one, is a hyperbolic tangent, which actually has a value between 1 and -1 instead of 1 and 0. So the Sigmoid one you have used, its range, it is bounded between 0 and 1, but the hyperbolic tangent, you can have a look at that, between 1 and -1. By allowing now the output of your neural network to go between 1 and -1, it tends to be trained, the learning tends to go much faster. There are other methods that also have been tested, like including a momentum term in your weight correction. So I would encourage you to read on that. These are other ways, other methods that researchers have looked into to accelerate the rate of learning. But the fundamental principle we've looked at here is a backpropagation algorithm based on the perceptron learning rule. So this was our breakthrough in the learning of MLP. And based on that, now you can read in the literature other ways that have been tested, especially the optimization methods that are applied now to bring the conversions quickly, but making sure you don't get stuck into local minima. Okay, so I'm stopping here now, and this concludes the chapter we wanted to cover on introduction to neural networks, where we've covered the perceptron MLP, training of perceptron, training of MLP. So now, based on that, you have, I think, the required background to go and read other types of neural network on your own. Thank you very much.